So for the past 2 weeks, we've learned how to use R and how to use R for data analysis, how to create models from R. We've seen several packages in R that we can use. So today we're going to be seeing how to, in addition to how to use, how to build models in R, we're going to be seeing how to use R to check for heteroscedasticity in regression models. Then how to use some of the available post-estimation tests and how to generate, how to use some script to check for heteroscedasticity, and as well as how to use a standardized and already standardized techniques called the push-pagan to test for heteroscedasticity. So let's start. So open your R. So like I said last week and last 2 weeks, is that there are several packages in R. Some packages are just, they are techniques, a collection of techniques for you to execute some work in your field, in different fields. So we have some techniques that can be used in engineering field. You have some that can be used in economics, in health, and so on. We also have some packages that are actually a collection of some data that has been used, right, in a textbook, right, like this Woodridge. So in the Woodridge package, it consists of several data sets that you can use in R. So, and each of these packages, they have a document. So that document tells you some of the functions in this package, and it tells you some of the ways you can use it. Several options are available. So for econometrics, of course, these packages, econometrics packages in R are just some of the econometrics techniques that we have been doing in our first seminar, second seminar, and all of that. So you see all of the provings, all of that, and from our advanced one as well. So today, what we'll be doing now is that I'm going to introduce you to some other packages again that we are going to be using to test for heteroscedasticity. But firstly, I want to clear my environment, my R environment, using this code. So that will remove everything here. It removes everything here. But if you want to remove it one by one, you just click remove brackets, one of these. But now I'm removing everything once and for all. So the first thing is to let's look at the question. The question says, using the Woodridge package and the data set called vote1, which is inside of the Woodridge package. So this data set called vote1 is more like an Excel, like a whole Excel file that has several variables. Say on the column, each column have several variables, right? So those variables have a name, they are named, right? So this particular Excel sheet now, or data, is called vote1, is in Woodridge. So we want to use this data set now to generate a model. So the model is trying to predict how I think the percentage of voters who vote for a candidate A as the dependent variable. And we have the independent variable called this priest LA, democ A, and the log of expend A, log of expend, so log of expend B. So that is, if candidate A spend, maybe your candidate A spend a lot of money on adverts and try to stimulate voters to vote for him. So if he spend more, is he going to get more votes by spending more? What about if his opponent spend more? That is the log expend B. If his opponent spend more, is he going to get more? Is he going to have higher percentage of votes, or will the vote he gets falls as his opponent spend more? So that's what we're trying to model here. So to start with now, we need to install the Woodridge package by typing install.packages, bracket, double column, Woodridge, and double column close, and bracket close. So with this, we install the Woodridge package into our R. Now the Woodridge package is installed. So the next thing to do now is to bring the Woodridge package now into our own library by typing library Woodridge. So with this, we're bringing the Woodridge package into our library. Like I told you, it's more like there are books that has been installed in this library already. But for you to use it, you pick the book and take it to your own personal library in your hostel. So something like that. So you bring the Woodridge package down into your own personal library. Then now that we have it in our own library, we now want to check the Woodridge package now and call a particular data set called vote1. So we call it more like after you've taken the book from the library to your from the big library now to your own personal library, using this library Woodridge. Now you want to check the book and look for some data set in the book to extract it out. So we use data vote1. So once we do this now, what happens is that the data will go to value under environment. Then, so the vote1 now is under value in our environment. So now the attach now is that we want to attach all the variables in the data set called vote1 into our search part, so that it's easy for us to be able to search for variables when you are trying to do the modeling. So what happens is that once you type, if I type P, for instance, it might suggest price and every other variable that starts from P. So I'm able to pick the one I need. So that's why we usually do this attach. So once you attach the vote1, which is a data set now, we go under data. It will leave values and go under data. Once I click attach vote1. So this will leave value and go under data. So now it's not under data. That means it has been attached. So the question one now is to do a regression of the percentage of voters on all the independent variables as asked in the example. So I have 4 questions here. So I'll be solving 2 with you. Then I will leave you to solve the remaining 2. So once you solve the first one, I will leave you to solve the remaining 2. Once you solve the first one, I will explain. And then after solving the second one as well, I will also explain. So after this example now, if you have any question, you can always ask. So you know how to generate a regression model in R, that is LM. LM means the linear model. LM means linear model. So vote A tilde, this tilde separates the independent variable, the dependent variable from the group of independent variable. Tilde separates the dependent variable from the independent variable. So you include new independent variable by just adding it with plus sign, right? So this is how to generate model in R. But we need to save this model in R so that in case we want to use the model again, it won't be lost. We can always go back to the model. So we assign this model to a space in R. So we call it reg1, right? Although you can call it anything you like, right? Maybe regression of voters or anything, or voters regret, anything you want here. You can always call it anything you want. So but what happened is that this enables us to save this model in R, right? Then to see the result of the model, you write summary reg1, right? So this reg1 is not a cast in stone. You can always change it to anything you want. So now let's generate the model by running this. You can always run it together or run it one by one. Then your result will show up in the console as is down left. But if the down left is very messy, right, like this, like what I have here, you can always clear everything you have here by clicking Control L. Control L. So it clears everything you have here. If it's messy and you want to clear it so that you can see the result clearly, you can just write Control L. So that clears everything here. So then I run the model. Now the result of the model is generated here. As you can see, what I have here now is only the result of the model. So let's try to interpret this result together now. The intercept shows, as you can see, 37.66 shows that candidate A naturally has the tendency to have some level of vote, right? Even if he's not doing anything, right? But one thing you also see that if he spend, the higher this is spending, the more the vote he gets, right? Because the relationship between the what he spent and the percentage of votes he's getting is positive. Then we also see that the spending of his opponent, candidate B, have a negative effect on the number of votes he gets, as we have minus 6.23784 here, right? And all of the coefficients are actually significant, right? So this 3 star shows that this is significant at 0.1%. 2 star shows that it is significant at 1%. Then 1 star shows that it is significant at 5%. So the next question now asks us to want to investigate if there is an evidence of heteroscedasticity in the regression. That means either there is a correlation between the error and the independent variables. So one way to do this is actually that we can actually estimate the error, the residual error, and we can regress the residual error on the independent variables. So when you regress the residual error on the independent variables, you are able to look at the R square. Once you look at the R square, you want to see the percentage of variation in the error that is explained by the independent variables. So now from our regression, let's estimate our residual error from the regression. So we call that let's call that resid. So that means from this regression model that we have, let's have one class, please. Let's have one class so that you can get, so that we can get what I'm trying to explain. And if you have any question, you can always ask at the end of these first examples. So now we want to generate the residual of the regression that we have. So we can have resid. So these resids that I have here, you can name it any way you want. You can call it residual. You can call it regression residual. So it's just a name. You can give it a name that you like. But the function to generate the residual from the regression is called resid. That's the function. Then the regression you want to generate the residual from, you put it into the bracket in front of the resid. And so we assign this function and the result of the residual that will be extracted from this regression, we assign it to resid. And we save it as resid. So we run that. That is generated now. You can see it in the values, resid. So now that we have the residual, the estimate of the residual, we can now regress the residual on the independent variables. This will allow us to be able to check the R square to see the variation in the residual that is explained by the independent variable. So that shows us maybe there's a correlation between the independent variables and the residual, right? So you see, we now have LM. So instead of having the dependent variable, we're going to have the resids there, right? So we are regressing the resid on the independent variable. So we can run this now. So we have the regression here. Now let's look at the R square. As you can see here, the R square here shows 6.145 exponent raised to power minus 32. So exponent raised to power minus 32 just means that this point after the 6, we have to shift it to the left 32 times, right? So once you shift it to the left 32 times, you're going to have 31 zeros in front of this 6. So approximately that means the R square is close to 0, right? So you have dots 0.00031 times before you get to 6. So it just means that the variability in the residual error, right, is not actually explained by the independent variables, right? And even if you go to the F statistics to see the F statistics, which shows the joint, the combined or the joint impact, right, of the independent variable on the dependent variable. As you can see, the p-value here shows that it's not significant, right? It's not significant. So that shows that there is no heteroscedasticity in the model, right? And in which model? The model is the first model we generated. That is this model that we have the LM of voters, vote A on all of the independent variable, right? It shows that there is no heteroscedasticity in this result. So that's what that is showing us. So as you can see the p-value of the F statistics here, and you can also see the R square here, giving us the same result. So, but now, instead of going through this long route to find out if the model has heteroscedasticity, and you know heteroscedasticity just means that the variance, right, is not constant. The variance is not constant. So now we want to use the Bruch pattern to test for heteroscedasticity. But before we can do that, we need to install some of the packages, post-estimation packages that we have in R. Then we are also going to be looking at generating the robust we are going to be generating the robust standard error as well. So because of that, we are going to install LM test, sandwich. I'm going to install zoo and foreign. So now let's install these packages in our R. So how do we install packages? Just install .packages, bracket open, double column, then the name of the package you want to install inside the double columns. So like I told you, all of these packages, they have their individual documents on R. You can go to R, you can type the name of the package. It will take you to, you can download the full document that explain the package, right? And you can also search under package here to look for some of the packages here, right? Then if you don't understand any of the package, you can look for help. You can go under help in your down right and check what's that mean under help, right? So now I'm installing this package in R. So now all the packages, the 4 packages, foreign, zoo, LM test, sandwich has been installed. So foreign is used to read data stored by MinTab, SAS, SPSS data, and several other statistical packages, right? The LM is used to testing linear regression model, as you can see. The sandwich is used for robust covariance matrix estimator, right? So the Woodridge package, you see, it has 115 data sets from the textbook Introduction Econometrics, a Modern Approach, 7E by Jeffrey M. Woodridge. So the zoo is an infrastructure for regular and irregular time series, right? So you can see that those, I'll give you a little summary of what those packages are for. So now, after installing this package now, we want to bring this package to our library so that we can use it. So you type library bracket, the packages, to bring it to your library. So, having done that, now we want to now do exactly what we've done before. Generate the model, then test the model with the push-pagan test, right? The push-pagan test is under the LM, I think the LM test. So it's one of the tests under the LM test package. So just generate the same model that you have generated before, but this time around now, we can now test the push-pagan to check for heteroscedasticity. Now I run the model, right? So let's see what the model, let's see the result of the model now. So you type summary. I saved the model as reg3. So let's type summary reg3. So the result of the model is here now. The same thing I generated before. But this time around now, let's, instead of regressing the error term, I mean the residual now on the independent variable to check for heteroscedasticity, I can just use my push-pagan test. it will tell me whether there is heteroscedasticity in the model or not. So I type my push diagram test here, BP test, bracket open, reg 3. So I get this result. So the result I have here, the push diagram is 9.0934, 4 degree of freedom. The p-value is 0.05881. But what we see now here is this p-value that we have here. Can we say this is significant or not significant? Anyone? Is the p-value significant or not significant? Anyone, please? Is it significant or not significant? So now let me explain the push diagram test. So the push diagram test is trying to check for heteroscedasticity. So it is also an hypothesis testing, right? So the H naught state that there is no heteroscedasticity, right? So it is not significant, there is no heteroscedasticity. So the alternative hypothesis, which is the H1, state that it is significant, and as such there is what? Heteroscedasticity. But what we have here now is 5.881%. So if you are looking at a level of significance of 5%, right, as your benchmark, this is what is significant. I mean, it's not significant because why? It is more than 5%. If it's less than 5%, where you have your alpha, your level of significance as 5%, then you say it's significant. But here now says that you have 5.8, and because it's higher than 5%, it is actually not significant. So if it's not significant, we accept our H naught. We accept the H naught and reject the H1. Right? So this shows us here now that there is no heteroscedasticity in the model. And if you remember, this is exactly what we got in the model we created earlier. The model we created earlier by regressing the resid. Can we have one class, please? Hi, can we have one class? Can we have one class? Please don't distract the people behind you. If you want to chat, you can always excuse us to chat. Let's have one class so that we can finish this thing in time, please. So, if you look at the regression of the resid on the independent variable, that shows us here we get a lot of indicator here that there is no heteroscedasticity. One, the R is close to 0, right? And the p-value of the F statistics also shows that it's actually not significant, right? So, but we wanted an easy route to get this result instead of going through that long process. And we use a standardized test by the push diagram to do that. And that still gave us the same result. But if your level of significance is 10%, then you'll be accepting here that there is heteroscedasticity. That is, if your level of significance is 10%. So, and now, how do you know which to choose? Whether to choose 1%, whether to choose 5%, whether to choose 10%, whether to choose 0.1% or 0.01%. So that depends on the data set you are dealing with, right? And the level of error, and the level of error you can accommodate, right? And it depends on the sector, the sector you are working in, right? So if you are working in the health sector, you'll be looking at something that is highly significant. You'll be looking at something that you have a high level of confidence. For instance, if you are working with, say, the COVID vaccine, for instance, we are looking at something that is very highly efficient, right? Maybe up to 100%. And if you cannot get 100% because human beings are not perfect, maybe 99%, right? So, and if you are looking at a confidence level of 99%, that means your level of significance is what? 1%. The level of significance is just like saying the error, the amount of error you can accommodate, right? So if you are looking at the aeronautic industry, you know that when people are inside the airplane, any aircraft at all, if there's any error, it leads to death, right? So you want a very high level of precision, right? In such case, you want the confidence level to be almost 100%, right? So, and if you can't get 100%, at least 99%, so you'll be looking at level of significance of 1%. But when you are dealing with social statistics, maybe you are looking at the health industry, you are looking at the economy, social economic statistics now, for instance, you can still accommodate 5%, right? You can still accommodate 5% in such situation. So that's why mostly you see that economists use 5% level of significance, because mostly they have 95% confidence level when conducting hypothesis. But that does not say that you cannot adjust. You can always change from 5% to 10 or 1%, depending on what you are working with. But commonly you see in economic journals, we use 5% level of significance. So with 5%, we are rejecting this, that there is no heteroscedasticity. Do we have any question on that? Any question? Any question before I move on? All right. So if there's no question, the question you want to ask is, peradventure we have heteroscedasticity. How do we solve it? How do we solve it? Peradventure we have heteroscedasticity. How do we solve it? So there are several ways to solve heteroscedasticity, the problem of heteroscedasticity. One way is to take the log. If you take the log of all of the variables you are dealing with, it makes it kind of stabilize the data, especially time series. It stabilizes it, and it's also easy for you to interpret, right? Because it becomes to us percentage change. That is the definition of your elasticity, right? So you said the percentage change in y as a result of the percentage change in x, right? And it also stabilize your series, and the issue of elasticity will disappear in some cases. So I think you will see that in the exercise you are about to solve now. So do you have any question before we move to the exercise? Any question? All right. If you don't have any question, then I think we can solve the exercise on our own. And if you have any question, you can always call me. So the exercise 1 and exercise 2. Let's start. All right. So I see some struggling with the question. It shows that some are not actually listening to the explanation. And if you have question, you can still ask for more clarity. Okay, attention please. So let me now do the correction for exercise 1. After that, then I will leave you to solve exercise 2. It seems some people didn't follow what we are doing actually, because I see people trying to install variables, install data sets. Some people are trying to install data sets. So the data sets are inside the package. The package is Woodridge. You can only install packages. You can't install data sets. So you have a package. Inside that package, you have data sets. Inside the data set, you have variables. Right? So you have a package. Inside the package, you have data sets. So data set is more like an Excel file. It has several variables in it, columns of variables. Right? So you can only install packages. You can't install data sets or install variables. So once you install package, you extract the data in the package by writing data brackets, the name of that data. Right? So in our case here, in exercise 1, the name of the data is hprice1. So you type data hprice1, right? Then you can attach it to your search part by writing attach hprice1. So the first thing to do is to install Woodridge package, then bring Woodridge into your library, then extract the data, this particular data from Woodridge, then attach it to your search part, right? And now, from my own side here, I have already installed Woodridge. I've attached Woodridge to my search to my library. I'll bring it to my library, so I can now bring the data hprice1, which is what we have here. I can now attach hprice1 to my search part, so it moves away from these values to data, right? So you can see it now under data. So now, so as not to mix things up, because I have regression 1, regression 2, regression 3 here. So what I want to do now is that I want to, okay, I feel like clearing everything, but let me just leave it that way. So once I generate another regression now, what will happen is that the result of that new regression, we overrun the old reg 1. Look at this reg 1 that I generated from the example. So the result of the new regression, we overrun the whole regression reg 1. So that's what's going to happen. So now, let me generate this regression that we are asked to generate. Run price on the lot size, on the square feet, on the numbers of bedrooms. So this model is trying to predict the price of houses from the lot size, the square feet, and the numbers of bedroom it has. So we expect that the higher the number of bedrooms, the higher the price of houses should be. We expect that the higher the square feet, the higher the prices should be. We expect that when the lot size increases, the price should increase. So we're expecting something like a positive relationship between the independent variable and the dependent variable. So now let's run the regression. So we have the regression here. As you can see, the result meets the a priori expectation. It meets our a priori expectation. That means, as you can see, it's positive. It's positive. We all have positive results here, right? So although this is very small, the lot size is very small relationship. It means take this point behind these two to the left hand side 3 times. So that's 0.002. This means 0.1. Why this means 13.8. 13.8. So we're taking this dot to the right once. And only the lot size and the square feet are actually significant. Right? The square feet significant at 0.1%. The lot size significant at 1%, as you can see. So now, we have this model, but we are trying to now generate the model with the robust standard error, right? We have our standard error here, right? So we now want to ask R, please give us. We have, this is the normal model. This is the normal model that we have, but we want the model with the robust standard error, more like saying the optimal model, kind of, right? So what we're going to do now is the robust standard error regression. So it's just the same regression as what we ran in the first one, but the difference is going to be that after running that now, instead of us saying the coefficient, the summary of regress 1 underscore robust standard error, we just run this coefficient test of the regression. The covariance equals to the covariance of, so this HC means the heteroscedasticity, right? Then the regression, the type shows us that then we tell R that it is from the sample, the data is from the sample. The data is not a population. So that it's used a correction. The correction it's used is, I think it's n minus k all over n minus 1. You multiply that with the error, right? So once you put this, so you can, if you want to use the normal one, that is to show that the normal one is HCO, but if you want to state R, that your data is actually a sample data, right? You use HC1. So now let me run the regression. I run the regression now. It's still the same regression, but now I want to get the regression with the robust standard error. So that gives us this result. So what we can now do now is we can compare the results, right, with the first result we have. So this is the model with the robust standard error. So once you include the robust standard error, you find out that the lot size is no longer significant, right? Only the square feet is significant. Although we have almost the same result, right? This is almost the same result. This is minus 21.7. This is minus 21.7 as well, right? We have almost the same result. Then the second thing now we can do now is to we can test the B-test to see if this model has heteroscedasticity, right? So let me do the B-test of the regression 1. So as you can see, the p-value for the B-test of regression 1 shows that the p-value is significant. The Push-Pagan test is 14.092, 3 degrees of freedom. The p-value is 0.0027. that is 0.27%. So which is actually less than 5%. So that shows us that what? There is heteroscedasticity in the model. So a way to remove the heteroscedasticity is actually we can get the robust standard error, the regression with robust standard error. Another way, we can also take the log of all the model, all the variables. Take the log of price, the log of lot size, the log of square feet, right? So to stabilize the data, the series. So once you take the log, what happens is that the variability in the series will be reduced. For instance, you might have some extreme values in the series. Say you have value like 5, 8, 10, right? So you might have some value that might be 105, right? So that shows that is an outlier, for instance. So what we want to take the log, it reduces the variability of that data, it stabilizes the data. So once you now run the regression, so the issue of heteroscedasticity will be reduced. So now take the log of the price, we call it LC. Take the log of the lot size, L lot size. Take the log of the square feet, L feet. But the bedrooms, they are already small numbers, right? Because what we are trying to achieve is to make all the big numbers to be small, to stabilize it. That's why you are taking the log. So, but the bedrooms, they are already in small numbers. So you have 1 bedroom, 2 bedroom, 3 bedroom, 4 bedrooms, a lot of that. If you check the variable bedrooms. So now if I take the log now, take the regression now, I run the regression, I have my reg 2. So now let's see the result of reg 2. So the result of reg 2 now is slightly different from the normal model and the model with the robust standard error. So without logging the dependent variable. But now I have the log of dependent variable here. So you can see that now after taking the log, the estimate changed. So we have minus 21.77 in the robust standard error model. But now that's for the intercept, right? Now for this intercept now, I have minus 1.29, right? So you can see that the coefficient change, then the intercept is now even is significant compared to the first two models that we generated. Now let's see this model now. Does it have heteroscedasticity as well, despite the fact that we took the log? So let's do the push pagan test of the regression 2 that was just generated. So the push pagan test, we have 4.2232, 3 degree of freedom. The p-value is 0.2383, that's 23.8, which shows that what? It is not significant. So there is no longer heteroscedasticity. So as you can see, that we had heteroscedasticity in the other models, but now after taking the log, the heteroscedasticity disappeared, right? After stabilizing the data, the heteroscedasticity disappeared. So do we have any question on this first exercise before we move to the last one? Any question? So you can see that using the logarithm transformation of the dependent variable often mitigates, and most times it entirely eliminates heteroscedasticity. So do we have any question? All right, if you don't have any questions, so let's move to the second exercise, the exercise 2. Let's move to the second exercise, the linear probability model. Linear probability model. We can start. So I believe we are now done with the linear probability model. So the exercise 2, I think we can do it together now. So the question asks us to download K401KSUB from Woodbridge Library. It contains information on net financial assets, NEFTA, family income, and a binary variable for eligibility in the 401k pension plan, which is called E401k, and several other variables. So the first question is, what fraction of family in the sample are eligible for participation in the 401k plan? So firstly, we need to import the data into our R. So the data set is K401K SUB. So exercise 2. So let's bring it in by writing data K401K sub. Because we have previously installed Woodbridge, so I might not need to install it again. So now we have it. So attach it to R. So it moves from value to the data. So now I want to see what exactly is within this data set. Let's see what we have in the data set. So we have those that are eligible for the 401k, income. We have several other variables, age, male, size, according to what we have here, the net financial assets, family income. So the first question says, what fraction of family are in the sample are eligible for the participation? So the variables of those that are eligible is shown as E401k. So 1, if it is 1, that means the person is eligible. If it is 0, that means the person is not eligible. So a way to do that is just to look for the mean. So that gives you the mean of E401k. So when you generate the mean, it gives you percentage of those that are eligible. So we have 0.392, that is 39% are eligible for the participation in the 401k. So the second question says, estimate a linear probability model explaining 401k eligibility in terms of income, age, gender, and we are asked to include income and age in quadratic form, right? So I think that will help us to see the maximum age of the eligibility or the maximum income of the eligibility when you include income and age in quadratic form. That means you include the square of income, you include the square of age, and also include the level of income, the level of age as well. So you have both in the same model. So let's build a model for that. And call it, let's call it regression 4. So let's call it regression 4 because we don't have regression 4 here. So reg 4. Of the eligibility tilde income, age, gender, the quadratic of age and income. So you have income, age, gender. Gender here is represented by male. So if it is male, the person is 1, female is 0. Then we are asked to include the quadratic form of income and age as well. So the income square, we have the income square here, income SQ. Then we have the age square, age SQ. Then we view the results by writing summary, reg 4. So now let's generate this model now. So we are regressing 401k, the eligibility for 401k on income, age, gender, income square, age square. So we have the results here. So we see that most of the variables are significant, aside from gender, right? The gender is not significant. So the higher the income, the higher the eligibility, right? The higher the age as well, the higher the eligibility. Most male, you can see, are not eligible, right, compared to female. Like I said last class, you interpret binary numbers with respect to the base. So the base are the ones, the base here are the ones that are in 0. Then for the income square, it shows you the threshold, for instance, as the base of the income of those that are eligible, right? And also the age as well here shows the minimum age for those that are eligible. So it's just the square. You just multiply this by 2. If you multiply this by 2, more like you are differentiating. You are finding the turning point to say the y, the x. So if this income is x, for instance, if you say the y, the x, so you have because it is squared, it will be 2 times the coefficient, right? It will be 2 times the coefficient. And that gives you the minimum income of those that are eligible. You can do the same thing for age as well. It gives you the minimum age of those that are eligible. So the next question says, would you say that 401k eligibility is independent of income and age? What about gender? Explain. So as you can see here, it's not independent of age and income, as income, you see, has a positive relationship with eligibility to 401k, and it is significant. So it is not independent of income. Age also has a positive relationship with the eligibility of 401k, and it's also significant. So we can't say it's independent, right? We can't say it's independent of income and age. But for gender, we can say it's independent of gender. As you can see, it is not significant at all when it comes to gender, right? So the next question asks us, obtain the fitted value from the linear probability model estimated in part 2. Are any fitted value negative or greater than 1? Use the predict command here. That is reg lm this, then predict reg. So basically we've generated the model already. So we can just predict the reg, we predict the regression, right? So now to predict regression, not just to predict, I want to save the result. You can save the result as y hat and say predict the regression, predict reg 4, and save it as y hat. So we now have that here, predicted. So the next question is now saying, are the fitted value negative or greater than 1? So how do you know that? You can take the summary, summarize it, so to see what we have inside the y hat now. Take the summary of the y hat. It gives you the details, some of the details in the y hat. As you can see, the minimum y hat is 0.02992. The maximum is 0.6. So it's actually not less than 0, and it's not greater than 1. So it's within the boundary of 0 and 1, right? In natural sense, for linear probability model, we expect that at times it goes beyond the boundary, right? So that's why in econometrics we move to probit and logit, probit model and logit model, because because of the linear probability tends to go beyond the boundary of 0 and 1, right? So now we are asked to add another variable. In the next question says, add the variable PIRA as an explanatory variable to the linear probability model. All things equal, if a family has someone with an individual retirement account, so PIRA is the IRA, individual retirement account, how much higher is the estimated probability that the family is eligible for 401k plan? Is this statistically significant from 0 at 10%? So we are asked to add this variable PIRA, that is individual retirement account, to the independent variable. Then we generate the regression again and see if the coefficient of PIRA now is significant, right? Then we also see the coefficient itself to tell us the proportion of eligibility for 401k, and to see if this coefficient is significant at 10%. You can see here now that we are using 10% here, right? We're not using 5%. So now let's do that. So basically, it's the same model that we generated before, only that now we include the PIRA now. Let's call it regression 5. Let's call it reg 5. So basically, I want to see the variable, how it is named. So I have the PIRA here. It's Control L. Control L clears everything here so that we can see clearly the result. Press Control L, everything here will clear. If it is messy, you can just clean it with Control L. So the coefficient of PIRA now is 0.0197, right? The exponential raised to power minus 2 minus 0.2 means that if you take the point to the left twice, 0.0197. So, and as you can see, it is not significant. So that means somebody with PIRA have possibility of being eligible for 401k. That's what the result is saying. But unfortunately, it's not significant. So the coefficient on PIRA means that all things equal, IRA ownership is associated with about 0.02 higher probability of being eligible for a 401k plan. However, the T statistics, as you see here, is only about 1.620, right? And under the two-side hypothesis testing, it is, we have the p-value 0.105. So PIRA is not significant at 10% level against a two-sided alternative. So once you are regressing under a linear probability model, you are regressing a binary variable, 0 and 1, 0 and 1, on other independent variable, right? The independent variable can be a nominal variable like, say, age, or a scale variable as well. So the results you get will become what? The probability of having 1, right? If 1 is eligibility, that someone that has 1 means the person is eligible, 0 means the person is not eligible, right? So all of this now is more like the probability of being eligible, right? So this now, if you take these points to the left once, this exponent means take this point behind this 5 to the left once. So that will be, the probability is, so this is the intercept, right? The intercept. But for the income, take the point to the left twice. So you have, the probability is 0.01, right? The probability is 0.01. So, do we have any question on the exercise? Any question? If you don't have any question now and you have question later, you can always send an email. You can always come for the office hour. Okay, someone raised hand for a question. Yeah, you can always come to the office hour in case you have any question. And I would advise that you practice this at home. The more you practice, the more perfect you'll be. Thank you.